Hello, everybody. Welcome. Well, let's look at the syllabus real quick together, see how things are laid out before we start lecturing. All right, we have okay, so this week we're working on solutions. And you'll have a solutions lab due on Sunday. Yeah, so we're doing solutions this week. Next week will be acids and bases and equilibrium. I think that we are going to, on Wednesday of this week, we aren't going to meet because the election's on Tuesday. We're going to just say that Wednesday is a mental health day for everybody. Okay, so you can use that time to do assignments. I will be around, so you're more than welcome to email me and we can chit chat about stuff, but we won't actually meet for lecture on Wednesday. Everybody okay with that? Or do you want to be hanging out with me on a Wednesday at noon? Probably not. Good with it. Okay, cool. So we may end up having to lecture a little bit on this stuff next week. Should be fine. Yeah, test will be next Sunday, not this Sunday, but next Sunday. Okay, so let's get started. This whole chapter is on solutions. So what is a solution? Over here, I've got a solution. Well, this person is making a solution of water and salt. So a solution is going to be a homogeneous mixture of two or more substances. Now, a homogeneous or homogeneous mixture, remember, is a mixture that's evenly mixed. So bananas and oatmeal would not be homogeneous. That would be a heterogeneous mixture. Homogeneous mixture, salt water, something where we have this consistent concentration throughout. And this will happen, these form when there's a sufficient amount of attraction between the solute and the solvent molecules. So in this mixture over here, the solute is the substance that we have that's and we have less of, or usually it's also the solid. If we have a solid and a liquid, the solute is what's getting dissolved. Okay, the solvent is usually the thing that we have a larger amount of. It's what's doing the dissolving. Now, when there's some sort of attraction between the solute, so in this case, it's the salt, and the solvent, which is the water, when there's an attraction between those two, and it is specifically if that attraction is stronger than the attraction between the salt and the salt, it will pull it apart and dissolve it. So down here we have, the larger component is going to be the solvent, the smaller component, or what we have less of, will be the solute. Now there's a bunch of different kinds of solutions. So solutes can be liquids, gases, or solids. So in some instances we have like salt water. That's where we have a solid dissolved in a liquid. But you can also have liquids dissolved in liquids, like alcohol. So when you have 60 proof alcohol, that's alcohol dissolved in water. You can also have gases dissolved in liquids, like a can of soda pop that has compressed gas in it. The solute, we will say that it's spread evenly throughout the whole solution. So the concentration will be consistent throughout the whole sample. And then the solutes are going to mix with the solvent so that the solute and the solvent have the same physical state. So salt would be solid, the water is liquid, but when we mix them together to create a solution, they're both going to have the same physical state. They can't be separated by filtration, but they can be separated through like evaporation. So if I wanted to get rid of the salt, I couldn't take salt water or a salt solution and pour it through a filter and get the salt removed, but I could evaporate the water and the salt would remain. That's one way to separate it. The solute, so whatever is getting dissolved, is not visible, but can give a color to the solution. So sometimes, I mean, not in the instance of salt in salt water, but there are other things that you can dissolve in water that will give it a little bit of a color change. So here is an example of copper 2 sulfate, which we used a couple times in 092 if you took that at AB Tech. When it dissolves in water, it'll give it this sort of bluish color. And it will break apart into its ions, so we'll have copper and sulfate. So here are some different examples of solutes and solvents. So if we have a gaseous solution where we have gas in gas or gas dissolved in gas, an example of that would be air. So we have oxygen and nitrogen mixed together. Liquid solutions where we see a lot of our solutions happening. We can have gas in liquid, so soda water. We can have liquid in liquid, vinegar, alcohol, those sorts of things that are dissolved in a liquid. And then solid in a liquid, seawater, or anytime we have like a salt dissolving in water. You can also have solid solutions. So brass is a mixture of zinc and copper. Steel is a mixture of carbon and iron. You mix the two metals together in a certain proportion so that you can get some of the properties of zinc and some of the properties of copper, right? You can get the strength of one and maybe the conductivity of another and so on. Water as a solvent. So water is one of the most abundant and common popular solvents out there. Sometimes they say water is the universal solvent because it can dissolve a lot of things. It can't dissolve everything though. It doesn't dissolve oil. So it's a polar molecule because we have this OH bond and they're not sharing the electrons symmetrically, right? So we've got a polar bond. So we'll have a positive dipole moment and a negative dipole by the oxygen. So because there's sort of a positive side and a negative side to it, this allows the water to stick to other water molecules. That's why water has a little bit of like a viscosity, or the water kind of sticks together. When you put water on like droplets on a leaf, you'll get these little like bubbles, right? It's not a single molecule of water, they kind of clump together. And that's because there's this attraction of water to itself because there's this polar, right? So the positive hydrogens will sort of adhere or attract to the negative oxygens. That polar quality also allows it to be sort of sticky or attractive to other polar things. So when are we going to form a solution? I kind of already stated this, but we're going to form a solution when the solute solvent, so the thing that's getting dissolved and the thing that's doing the dissolving, the attraction between those two things is greater than the attraction between just the solute with itself or the solvent with itself. And then this is a really good one to know, likes dissolve likes. So polar materials will dissolve polar things, all right? So water is really good at dissolving polar materials. Oh, excuse me. It's not very good at dissolving non-polar things. So some examples of non-polar things, all of like our organic stuff, not all of them, but a lot of the organic stuff like oils, those are non-polar. That's why water won't dissolve your oil or your grease, right? If you have a greasy stove after cooking something, you can't just put water on it and expect to wipe it up. You'll just sort of smear it around. What do you have to do? You need to add some sort of soap to create a bind between the polar water and the non-polar material. So a good rule of thumb, likes dissolve likes. So solutions with any sort of ionic solute, and this goes for anything that creates like an aqueous or is aqueous. So we've got NaCl as kind of our go-to, but this is a solid. If we hydrate this thing or we put it in water, add water here, it will break apart into its ions. So we'll have little sodium with the plus charges floating around and little chlorines with minus charges, and they're actually separated in solution. And you can see over here that the little sodiums are sort of blocked by the water molecules. The positive charge of the sodium is attracting the negative oxygens or vice versa. The negative oxygens are attracting the positive sodium. And then the positive hydrogens are kind of clumping around the chlorine. If I wanted these two things to come back together, the sodium and the chlorine, I could evaporate all the water molecules, and then these two things could come back together into a ionic lattice structure. So solutions with polar solutes. So we've got this thing here. This is methanol. It has this OH group sticking off of it, and this makes it asymmetrical or not really balanced. So let me draw the structure of this thing. So this guy looks something like this. We'll have carbon with a hydrogen, a hydrogen, a hydrogen, and then one of the groups is an OH. Okay. So it's not very balanced. There's an asymmetry to it, which means that there's a polar quality to the molecule. Anything that has this asymmetrical sort of appearance to it is going to dissolve in water. So here's our methanols, and they are going to adhere to the water molecules. So this will dissolve. Instead of methanol, if we looked at methane, C, H, 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 and H, look at how this thing is very balanced, right? All of them have equal partners. This means this molecule is non-polar. This is non-polar. This is not going to dissolve in water. This guy here is polar. So when you're trying to decide if something's going to dissolve in water or not, you want to see if its structure is like balanced looking, or if its structure is unbalanced, or if it has a polar or a non-polar quality to it. So looking at these, we want to identify which one is the solute between the two of them. So again, remember the solute is going to be what you have less of, or it's whatever is getting dissolved. So you have 2 grams of sugar and 100 milliliters of water. I would say the solute for that is sugar. That's what's getting dissolved. The solvent, what's doing the dissolving, would be the water. We have 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. In that case, the 30 milliliters of methyl alcohol is going to act as your solute. It's whatever you have less of. It's getting dissolved in the greater quantity of the 60 milliliters. Over here, we have 55.0 milliliters of water and 1.5 grams of NaCl. The NaCl is getting dissolved in the water. And then air, we've got 200 milliliters of oxygen and 800 milliliters of nitrogen. We would say that the 200 milliliters of oxygen are the solute because there's less of it. A pretty easy rule of thumb with that. Okay, so looking at this here, when solid lithium chloride is added to water, it dissolves. And the reason that it dissolves is because we get this Li plus and this Cl minus. So these are the ions that we expect to see. Now the Li plus ion is going to be attracted to the oxygen, which has the negative dipole charge. All right, so 1 is for A. The opposite is true of the chlorine. The chlorine is going to be attracted because it has a negative charge, just like opposite ends of magnets. It's going to be attracted to the hydrogen atom, or the positive end of the water. And that's true for all ions. The negative is going to get attracted to the positive hydrogen. The positive is going to get attracted to the negative oxygen in each water molecule. So looking at each of these, I want you to tell me if you think that it would dissolve in water and why. Okay, so I'm gonna have you try and play around with this. Really based off of, is the thing polar or non-polar? Okay, so for this first one, I would guess that this thing is going to dissolve in water because it's an ionic compound. Now, just to be fully transparent, there are ions or ionic compounds that don't dissolve in water, right? And you would need to look at a solubility chart. But for the basic rule of thumb that we've been talking about, this is ionic, it will dissolve in water. Gasoline, B, it tells us here that gasoline is nonpolar. So I would expect that gasoline is going to repel water, or it's not going to dissolve in water, right? Likes dissolve likes. 3, I2, I'm going to say that this isn't going to dissolve in water. Why? Because this thing is nonpolar. Nonpolar. Why is I nonpolar? Well, this is really simple drawing. I bonded to I, right? They share the electrons equally. So this is a nonpolar covalent bond. They're sharing the electrons, but they're balanced out, right? So no dipole moment happening here. So we would expect that guy to, that wouldn't dissolve in water. This last one here, I would say, yeah, that definitely is going to dissolve in water. The hydrogen and the chlorine, so hydrogen bonded to chlorine, they will not share the electrons equally. The electrons are going to stay a little closer to the chlorine. So this will dissolve in water. So which ones dissolve? This guy and this guy. Any questions on that? No, it's sort of pulling in that last chapter or a couple chapters ago where we were talking about, is it ionic? Is it polar covalent or non-polar covalent? So you want to keep that in mind when looking at some of these. All right, so electrolyte and non-electrolyte solutions. Electrolytes are a really important thing in our body. They help us to maintain a lot of different biological functions in cells and organs. Here's a bag of an electrolyte solution that they're going to administer to a patient. So different types of electrolytes that we would expect to see: sodium, potassium, chlorine, bicarbonate. These are all charged particles. So when I say sodium, I don't mean Na. I mean Na with a plus charge, right? That makes it the electrolyte solution. We need these things. If our electrolytes run low, things get kind of funky, right? Sometimes it's not enough to hydrate your body with just water. You want to drink an electrolyte solution like Gatorade. And when they say Gatorade has electrolytes and you spend all this money for it, it's really just dissolved salt water. That's all it is. So we can separate electrolytes as solutions into either strong electrolyte solutions or weak electrolyte solutions. In a strong electrolyte solution, the material will completely dissolve in water. So NaCl is an example of a strong electrolyte solution. It completely breaks apart. So every NaCl is going to break apart into Na and Cl minus. If we were to run, let's say we were to try and light a light bulb with a strong electrolyte solution, we'll be able to pass a current through the solution because there's these charged particles that will allow an electrical current to run through. If this happened to be pure water, there weren't any electrolytes in it, it was just H2O, we actually wouldn't be able to run a current through it, all right? Weak electrolyte solutions, these things only dissociate partially in water. So HF is an example of a weak electrolyte solution. Some of the H's and F's will break apart, but if you see there's a double arrow here, which means that some of the H's and F's will actually recombine. So there's a percentage of the HF and there's a percentage of the H and the F's broken apart. We'll find both the molecular and the ions in solution. Because of this, we have less charged particles floating around in solution. So our current is not going to be quite as strong. So we'll actually see, we can actually see this in a lab setting where the light bulb will not, it'll be a lot dimmer. And there is an experiment that we would normally run if we were meeting where I would put a light bulb with a current into different solutions, and things that are weak electrolyte solutions will again give you this dim color. If it's a strong electrolyte solution, you'll get a really bright light. One way to identify from an equation if it's a strong or weak: strong will have the arrow moving just towards dissociating or breaking apart. A weak will have arrows pointing in the dissociated direction and also the recombination. And this is known as an equilibrium equation, and we'll talk a little bit more about that in the next chapter. Here's a non-electrolyte solution. So I've got sugar as a solid, I add it to water, and it does dissolve, but it doesn't break apart into ions. It just breaks apart from the other sugar molecules. Whereas here, our ions or our molecule is actually breaking into these charged particles. Here, the molecules are just separating from each other. They're just creating space from each other. So there's no charged particle here. So when sugar gets dissolved into solution, we don't find positive and negative ions. We won't be able to run a current through this. So they don't conduct electricity. So know the difference between these. Here are some examples of weak electrolyte solutions. We will talk a little bit more about specifically weak acids, which tend to be our weak electrolyte solutions when we get into the next chapter. All of your molecules or your molecular compounds like methanol or anything where they're sharing electrons, where it's not a metal, non-metal combination or ionic, is going to be in this non-electrolyte. Right, our ionic stuff can either be dissociates completely or a weak electrolyte, or it may also be something that doesn't form an electrolyte because it stays as a precipitate. So if we're looking at this here, complete each reaction for a strong electrolyte solution. So in this case, we're going to assume that these completely break apart. So if I'm going to break these apart, calcium is going to break apart into a 2+ charge. So we don't want this thing because we're saying it breaks apart. So we don't like that first guy. I don't like him. I do like this and I do like this because we're going to get this Ca2+. Now I have to figure out what happens with my chlorines. Well, in this case, I like C. I'm going to go with 2 Cl minuses. Now you may be saying, well, chlorine is a diatomic molecule. Yeah, but in this case, we're not introducing chlorine as its elemental form. We're introducing it as a charged particle. Okay, when it's charged, it doesn't bond to itself. So I don't like this. I do like this. What I'm saying is I have 2 charged chlorines, right? And 1 charged calcium with a 2+ charge. Looking at this, if I'm going to break this thing apart, I have 3 potassiums. So I like this right here. I don't like that one. Ugh, go away. We do like that. I also like that. But this polyatomic is not going to break apart. When we break that apart into its ion, or when we break this apart into its ions, this is going to stay as a group. Why? Because the connection between the P and the O is very, very strong. Those aren't going to break apart from each other. So we don't like this. We're going to keep our polyatomics together. So looking at this, which of the following reactions represents the dissociation of a strong electrolyte solution in water? So the only thing here that's showing us a solution, this is just taking a hydrocarbon that's a liquid and dissolving it into aqueous form, but we're not separating it into its ions. Same thing with this one, right? It's a liquid and then it becomes aqueous. So we're not actually separating it to its ions. Same thing here, we're grouping it together. C is really the only thing where I've got a material and I'm breaking it apart fully into its ions. It's got to break into the ions in order to be an electrolyte solution. And it needs to fully break apart, so arrow in one direction if we want it to be strong. All the other ones are dissolving, they're just not creating ions. So let's do this one. We've got, yeah, let's do these. I want you to write an equation for each of these things. So the first one says, we're going to dissociate this potassium chromate in water, and it's a strong electrolyte solution. B, we're going to partially dissociate this weak electrolyte solution. And then C, we've got solid sugar, and we're just going to dissolve sugar. So I want you to write the equation for that, or what the before and the after is. And if you want above the arrow, because you've got your starting and your ending above the arrow, you can put H2O with a little liquid sign to let you know that, or let the reader know that you are transitioning by putting it in water, changing it by putting it in water. All right, so for this first one, oh, come on. My pen has been giving me a really hard time. Okay, so we've got K2CrO4, and this is a solid. And it's telling us it's a strong electrolyte solution. So I know that I'm going to have an arrow just going in one direction because everything's going to break apart. I'm adding H2O. So I'm going to put that above my little arrow. Now I need to break this apart into its ions. So I have potassium, and I actually have 2 potassiums. So I'm going to say 2 potassiums with a plus charge, and this thing is now aqueous. That's how it's changed. I've also got this chromate ion, CrO4. I got to put the charge in, 2 minus, and it's aqueous as well. All right, both of those have dissolved. I'm not going to put an arrow going back in the opposite direction. Good with that one? Where all those numbers are coming from? Okay. Next one, partial dissociation of a weak electrolyte. So H3PO4. So it says this is aqueous. It's partially dissociating, which means I'm going to put an arrow going back and forth because some of it's going to break up, some of it's going to recombine. In this case, this isn't something we have talked about just yet, but all the H's aren't going to come off at once. Okay, when we have an acid like this, we take the first H off, and then the second H, and then the third H. All right, so if you put 3 H's, that's okay. This is actually what I want it to look like: H plus, aqueous, plus H2PO4 minus, aqueous. All right, because we stripped the first hydrogen off, we would go through another process, another reaction to strip the second hydrogen off. If you had put 3 H pluses plus the PO4, 3 minus, I don't fault you for that because we haven't talked about that yet, but that's not actually what's happening because we don't strip all the H's at the same time. Aqueous. Arrow, important thing, arrows going back and forth. Some of it's breaking apart, some of it's recombining. This last one here with solid sugar So we've got C12H22O11. It's a solid. I'm going to put an arrow because it completely dissolves, H2O liquid. And we're not breaking this up. The only thing we're doing is changing its phase. 22O11, sorry for the handwriting. Instead of it being a solid, now it will be aqueous or dissolved. All right. We don't end up with any ions. So if I was looking at these three, wondering which one's going to be most effective electrolyte solution, it's going to be this one, then this one. This is a non-electrolyte solution. It doesn't give us any charged ions. So how do we measure this like quantity of charge or how much electrolyte we're getting in a solution? Because you don't want to, if you're giving a patient a bag of electrolytes, you don't want to give them too much electrolytes. You don't want to give them too little electrolytes. So we use this thing called an equivalent or an EQ. An equivalent is the amount of an electrolyte or an ion that provides 1 mole of electrical charge. And that could be either positive or minus. So it does depend on, your equivalent will depend on what the charge of the ion is. If you're dealing with sodium, which has a +1 charge, it's going to be different than if you're dealing with magnesium with a 2+ charge, all right? Now the charge of the positive ion is always going to be balanced to the charge of the negative ion. So when you've got a solution, you can assume that you've got equal charges. And then the concentration of the electrolyte, when we're using an intravenous fluid, we'll use these things called milliequivalents per liter. And what is a milliequivalent? That's just a normal SI prefix, right? So 1 equivalent is equal to 1,000 milliequivalents. Just like 1 meter would be 1,000 millimeters. So we've got this milliequivalent per liter, which is useful in the medical field. So let's look at some different equivalents. All right, if I have sodium, it has a +1 charge. So I would say the number of equivalents in 1 mole would be 1 equivalent. Okay. Now that's different than calcium. Calcium has a 2+ charge. So it actually has 2 equivalents in every 1 mole. So it's like you get more bang for your buck, the more charge you get, okay? 3+ is going to give us 3 equivalents. Same thing with the minus charges. A chlorine with a -1 charge will have 1 equivalent. It's the opposite charge, right? It's a negative charge, but it's still considered 1 equivalent. Sulfate, treat your polyatomic like we have for most of the semester as a packet. That charge is talking about the whole packet. So we would say there are 2 equivalents there. So if we look at an example here, if I've got a solution and it contains 25 milliequivalents per liter of Na plus and 4 milliequivalents per liter of K plus, we would say that the total charge is 29 milliequivalents per liter, or you add the 2 individual amounts together. So in an electrolyte solution that you're administering to a patient, you don't always just give them sodium. You don't always just give them potassium. A lot of times they're a mix of the 2, and you can just add those equivalents together. Now, something had to deliver that positive charge, or we have to have a counteracting negative charge. So if we delivered those sodium and potassium with chlorine, chlorine would also have to have 29 milliequivalents, right? Or whatever your negative equivalent is, it has to equal the positive equivalent, and vice versa. So if we look at this example problem here, the laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents in every liter. And this says how many moles of calcium, or how many moles of the calcium ion are in 0.50 liters of blood. So if we're dealing with calcium, calcium has a 2+ charge, right? So for every 1 mole of calcium, I should be equal to 2 equivalents, right? That's what that says. Every mole of calcium, let me put a 2+ charge there, gives me 2 equivalents. So I have that. I also have this, my given information, which tells me that I have 0.50 liters of blood. And then I also have this here. I know that there are 8.8 milliequivalents in every 1 liter. So I start with my given information here, which is this 0.50 liters of blood. And I'm going to use this relationship that tells me that for every 1 liter of this patient's blood, they have 8.8 milliequivalents of calcium. So the liters will then cancel. Now, for every 1 equivalent, I have 1,000 milliequivalents. Right? This is that basic prefix relationship. So now my milliequivalents will go away and I figure out how many equivalents of calcium I have. And in this case, I have 0.0044 equivalents of calcium. But it doesn't want to know equivalents of calcium. It wants to know moles of calcium. So how will I calculate that? Well, I use this thing right here, which says for every mole of the calcium, it's equal to 2 equivalents. So I have my equivalents, 0.0044 equivalents of calcium. I multiply it by that relationship that says 2 equivalents for every 1 mole, and we're able to get our molar value. Or we can find out that in this person's, if we have half a liter of their blood, we would expect to see 0.0022 moles of calcium. So let's do one more of these. Very similar problem. Okay, so lab tests indicate a blood sodium level of level 5.3 equivalents per liter. Well, let's change that. I'm going to say that's a high amount. Let's go with 0.053 equivalents per liter. How many moles of sodium are in 350 milliliters of blood? Okay, so similar to the last one, slightly different, but lab tests indicate a blood sodium level of 0.053 equivalents per liter. How many moles of sodium are in 350 milliliters of blood? Okay, so looking at this problem here, we're talking about sodium, and it says that we have a blood sodium level of 0.053 equivalents in every 1 liter of blood. How many moles of sodium are in 350 milliliters of blood? So we start with our 350 milliliters. Now this is a relationship between equivalent and liter. So I want to get that out of milliliters and get into liters because it's kind of useless if it's in milliliters. So for every 1 liter, I have 1,000 milliliters. All right, that'll get my milliliters gone. Now what I can do is relate liters to how many equivalents I have. So 0.053 equivalents, that capital E, for every 1 liter of blood. So the liter cancels, the milliliters cancel. Now we're talking about sodium. So in this instance, the relationship between moles and equivalent is going to be for every 1 mole of the sodium, how many equivalents will I get? 1 equivalent, right? EQ, because its charge is 1. So you only get 1 positive bang for your buck. So in this case here, 1 equivalent for every 1 mole, or a 1-to-1 ratio. The equivalents will then cancel. And in this case, we end up with 3 times 0.053. Come on. I got 0.019 moles of this ion. Give you just a minute to write that down. Okay. So let's look at a couple other questions talking about this equivalent thing here. One thing it says, the laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. If chloride is the only other ion present, what is the concentration in milliequivalents? Well, if your positive thing is 8.8, your negative thing will also have to be 8.8. They have to equal each other. So here are some typical concentrations for equivalents in blood plasma. Don't have to have these memorized, but do notice how your positive ions, here are all your milliequivalents, about 150 milliequivalents for your positive. Your anions also have to be 150. Here's some intravenous solutions, different equivalents. Let's look at this though. So if you have 1 mole of Fe3+, how many equivalents would you expect to have? So 1 mole will yield, drum roll please, 3, right? So it's whatever the charge is going to be. This one is asking us something a little different. It says, hey, you have 2.5 moles of this. What is the number of equivalents? We'll start with the 2.5 moles. And we know that in this instance, for every 1 mole, how many equivalents are we going to get? 2 equivalents. So we'll multiply those 2. End up with this. An IV bag or bottle contains sodium chloride. If sodium has 34 milliequivalents, the chlorine also has 34 milliequivalents. Just how it goes. Okay. So looking at solubility, this is a picture of somebody who has gout. So they have too much, specifically uric acid in their solution. So what ends up happening is the uric acid will start to actually precipitate out into like a solid in the joints. So yeah, anytime you have a concentration of this uric acid that surpasses, like they have 7 milligrams for 100 milliliters, you're going to start to get a precipitate. So when we're talking about solubility, like how soluble something is, solubility is going to be the maximum amount of solute that can be dissolved in a specific amount of solvent. So how much solute can you pack into that solvent? Everything has a certain amount of solubility, and it is dependent on temperature. So for instance, salt, right? You can only dissolve so much salt in water. At some point, you're going to start to max out the solubility, and you'll get salt just sitting at the bottom of your container. We're going to express this thing in grams of solute for 100 grams of, in this case, water. Solvents usually water. Can you have solubility for other substances? Yeah, but what we're going to be talking about for most of this will be in reference to water. So if you are in an unsaturated solution will contain less than whatever the maximum amount of solute is. So let's say you can dissolve 36 grams of salt in 100 grams of water. Well, unsaturated would be anything less than 36 grams, 35.5, 35.9, 1 gram, 2 grams, whatever, anything less than that. It means that there's still room to stick more of the solute in. A saturated solution contains the maximum amount of solute that can be dissolved in solution. You'll have some sort of the undissolved solute sitting at the bottom of the container. And in this case, we've got solute and solvent. It's coming together, and we're getting this sort of dissolving and recrystallizing. So some of it's dissolving, some of it's recrystallizing sort of over and over again. There's this transient component to it. But you will have this hunk of solute sitting at the bottom. Why? Because this amount of water can't dissolve this. If I wanted to dissolve this stuff sitting at the bottom, I would have to put it in a bigger container with more water because we've maxed out our solubility. So if we were to label each of these as saturated or unsaturated, the salt disappears when you put it in the water. We would say that solution is unsaturated because it can accept or receive more of it. Okay, so sugar added to a cup of water that does not disappear but sits at the bottom of the cup. That means you've added way too much sugar to your tea. Okay, if the sugar will no longer dissolve in your tea, you may want to re-look at that. But that would be a saturated solution. Your tea would be saturated in sugar, and any additional sugar is just going to sit at the bottom. Okay, I've had that happen once or twice before, though, when I've had like a really sweet tea. So know the difference between saturated and unsaturated. Saturated can't receive any more of the solute. Unsaturated, you can pack more in there. So let's look at these combinations, okay? And these are temperature dependent. So this says we're at 40 degrees Celsius, and all of these scenarios are also at 40 degrees Celsius, so we can kind of just ignore the temperature. So KBr, normally, at 40 degrees Celsius, it'll hold 80 grams of the KBr in 100 grams of water. That's pretty high solubility. So we want to look at these solutions and determine, are they saturated or are they unsaturated? So this first one here says, hey, you got 60 grams of the KBr in 100 grams of water. Have you reached your maximum amount it can hold? No, it can hold 80. And we're only at 60. So we're going to say this first guy is unsaturated. All right, the next one is saying that you have 200 grams of KBr in 200 grams of water. And ours is in reference to 100 grams of water. So what I'm going to do is just divide both these values by 2 so that I can get it into the relationship that we know it as. So this becomes now 100 grams of the KBr in 100 grams of water. Looking at that in comparison to what we know our solubility, that is saturated. There's too much of the KBr in what the water can hold. So we would say saturated. This last one here says 25 grams in 50 grams of water. Again, I'm going to get it into these units specifically the 50 grams, I'm going to move that to 100 grams. How do I do that? I'm going to multiply each of these by 2. So 25 grams and 50 grams of water is the same thing as saying 50 grams in 100 grams of water. You guys see how I did that? Just so that I can sort of compare them. So the ratio makes more sense. 50 grams and 100 grams of water. Oh, we're definitely below our saturation level. So I'm going to say this is unsaturated. And remember, that can change with temperature, but since we're all at 40, we can just sort of ignore the 40s. So, oh yeah, I was like, what are we talking about? Okay, so let's talk about solubility in reference to temperature. So there are 2 different things that you have to take into account. Are you dissolving a solid in a liquid, or are you dissolving a gas in a liquid? If you're dissolving a solid in a liquid, your solubility increases with an increase in temperature. So hot water can hold more salt than cold water. Water at the equator is much saltier than water in the poles because it can hold more salt. The opposite is true for gases. The gases are not on this diagram. This is referencing solids. Gases, their solubility decreases as you increase in temperature. So think of this one as salt water. Think of this as soda. How do you like your soda pop served? Usually you get your soda pop or your beer served cold. Why do we have our soda cold? Because when it's cold, it can hold the gas. The gas will stay dissolved. When it's warm, your pop's going to get fizzy really quickly because it's going to lose all of that gas. So solids, as we increase the temperature, we increase solubility. Gases, as we increase the temperature, we decrease solubility. Warmer things hold less gas, but more salt. So looking at this, okay, why could a bottle of carbonated drink burst or explode when it's left in the hot sun? So if you leave, a can of Coke in your car, it can burst because all of that carbonation comes out of solution. It's no longer dissolved in the liquid. It becomes its gaseous form. And when it becomes a gas, it expands drastically. When it expands, it will bust the can open. Why do fish die in water that is too warm? Well, warm water cannot hold as much dissolved gas. So there's less oxygen dissolved in warm water than there is in cold water. If you have less oxygen, the fish have less water or have less oxygen to breathe and they'll die. So fish do breathe oxygen like we breathe oxygen. They just can actually extract it from the water. So pressure also has an effect on solubility, specifically solubility with gases. So we have this law called Henry's law. And it states that the solubility of a gas in a liquid is directly related to the pressure of the gas sitting above the liquid. So if there's a lot of pressure sitting above your liquid, a lot of gas can stay in solution. If your pressure is released above the solution, you lower that pressure, less gas sits in solution, or the gas is easier to escape. So you can think of this as a closed can of pop that's under pressure. So here there's like a lot of pressure sitting in the gas that's above that liquid. So a lot of gas can remain dissolved. As soon as I lower the pressure or I open this can and this gas pressure decreases, a lot of this gas can then come out of solution. So that's why when you have like a clear can of Coke, when it's closed, you don't see the bubbles. Right? It's only when you open it that you then start to see the bubbles because it starts to degas because of this, this law here. right, so there are some salts. There are certain salts that are soluble. A lot of ionic stuff is soluble, but there are a couple things that aren't. A lot of times, if you have something like chlorine, bromine, or iodine, and they happen to be combined with silver, lead, or mercury, these are insoluble. They'll form a precipitate. Same thing with sulfate. If it's combined with any of these things, it tends to be insoluble. These are things that you would have to have access to a solubility chart. I wouldn't expect you to have these memorized, but do know that there are some ions that do form solid. If you stick them in water, they'll form a precipitate. So sometimes if you mix certain aqueous solutions, you can produce an insoluble salt. Barium sulfate is an insoluble salt used to enhance x-rays if you're looking at x-rays of digestional tracts and things like that. Again, here's some more. Okay, this is soluble. This is soluble. This is insoluble. Why is it the case? Because it's on a solubility chart somewhere. There's no real quick rule of thumb. I mean, I guess one thing you could do is everything in column 1, if it's mixed with sodium or potassium or lithium, those tend to be soluble. Column 2 is a little bit more varied. But outside of that, you just kind of have to memorize them or look at the solubility charts. So what ions make each of these compounds insoluble in water and why? Again, I'm not going to test you on the solubility rules. It's kind of pointless, but this one is insoluble because of the lead combined with iodine. It's just these two specific mixtures, that sulfur. The sulfur tends to make those insoluble. The nickel with the OH, generally insoluble. All right, so solutions are different than formulas in that, when you have salt, NaCl, built within that is its recipe, right? You have 1 sodium atom for every 1 chlorine atom. In this case, we've got potassium iodine. That is a formula. We know that for every 1 potassium, we'll have 1 iodine. When I'm making a solution, I'm taking that and I'm mixing it with something like, let's say, water. Well, now I have to express that solution in a value known as concentration. How much of the solute is given in the solution? I don't talk about concentration when I look at a formula on its own because, in order for it to be potassium iodine, it's 1 of these for every 1 of these. But if I take this and dissolve it in water, I've got to let the reader know how much of this stuff did I dissolve in water? Did I dissolve 1 mole? Did I dissolve 6 moles in a liter of it? How do I do that? So I represent that using concentration. So there are a couple different ways to measure concentration. It's expressed as the amount of the solute over the amount of solution, all right? That always throws people off. It's not solute over solvent, it's solute over the total solution. Now we can look at it as a mass percent, a volume percent, a mass volume percent, or this thing called molarity, which we tend to use the most often. I think molarity is the most useful. We'll go through each of these. But remembering, bottom thing is talking about solution as a whole. So mass percent is going to be the concentration of a solution by the mass of the solute over the mass of the entire solution, okay? Or grams of solute plus grams of solvent. Mass percent can also be written as grams of solute over 100 grams of solution if we're given the mass percent. You can kind of work backwards between those two. Okay, so I'm going to give you a problem. You have 8 grams. Oh, there we go. Okay, 8.00 grams of potassium iodine dissolved in 50 0.00 grams of H2O. I want to know what the mass percent is. Okay, so for this one, we're going to take, to find the mass percent, that's going to be equal to the mass of the solute over mass of solution. Now the key thing here being the mass of the whole solution. So my mass of solute is going to be the 8.00 grams. The mass of the solution is going to be that and the 50 grams added together. So it's actually going to be 58.00 grams times 100, sorry. Multiply this by 100 to get it into mass percent. So if you went with 16, you weren't reading the problem exactly the way it needed to be read. So we've got 8 divided by 58. And if we end up with 13, I got 13.8 grams. Come on. Oh, come on, just work for me here. 5 minutes left. You can do it. Okay. So this is 13.8%. I'm going to ask this question in a slightly different way, because this is, hey, 8 grams of Ki dissolved in 50 grams of water. Well, what if instead we said something like this? Here, this is asking it in a slightly different way. When water is added to 8 grams of KCl, well, this I guess is talking about KCl instead of Ki. To form 50 grams of a KCl solution, the mass percent is 16%. So the same numbers, but instead the writer or the question is specifically saying you have 50 grams of the solution. So what you need to be looking at is this telling you the solution, or is it just telling you the value of the solute? All right, if it's just the solvent, if it's just telling you the value of the solvent, then you need to add it to the solute's value. If it's telling you, hey, I added until I got to a total solution value, you can just run with that as your denominator. All right, so let's try this problem here. A solution is prepared by mixing 15 grams of Na2CO3 and 235 grams of water. Calculate the mass percent. Okay, so for this one, hello. All right, so this is a situation where, you got to read the problem. The solution is prepared by mixing 15 grams of this and 235 grams of H2O. So it doesn't give you the mass of the solution. It gives you the mass of the individual things. So we're going to want to take the mass of our solute and divide it by these two components added together, right? Because our bottom value is solute plus solvent. So 250 grams of solution in total. So we take our 15 grams and divide it by that 250 grams and multiply it by 100, and we should end up with 6%, or 6% of solution is Na2CO3. So we'll get into volume percent next time, and molarity next time. So we'll stop there. So I won't see your faces until next Monday. Have fun, stay safe out there. Again, Wednesday is going to be an election mental health day. So you can work on things as you see fit. I will be around though, so email me if you have questions on any of those days. I don't want you to feel like I've just left you for the next week, but yeah, that's all I got. So have fun, bye, stay safe. Lauren, it's only my class. I mean, maybe you have other instructors who are not meeting for class. I just know that, like, for me mentally, I'm not going to be in a great place either way. So we're just not going to go there. But Lauren, yeah, but do honor your other classes if your instructors are having you be there. You won't have to be with me though. For lab on Sundays, or Janine, I think I might, I might end up moving the lab day. Janine, will you send me an email to remind me, and I'll push the lab back till sometime in mid next week. Cool. Yeah, send me an email like now, and then I'll just bank it and figure that out in the next couple of days. Okay. Cool. All right. Looks like there's some people who might have questions. Whitney, you're still having surgery. Okay, no worries. Thanks for letting me know.